no airani me haina o ko tupuna, ko Sullivan, toko whānau, ko Waipapa tamata rau toko hapori, e noho ana o ki naha whenua me nā wai tapu o Ngāti Whātua. Tēnei ka mihi, tēnei koutou, tēnei koutou, tēnei koutou katoa. Kia ora everyone. I just explained again, in case you missed yesterday, I'm John O'Sullivan, and I gave my place in the world, saying where my ancestors are from and what part of New Zealand I call my home. My ancestors are Irish and Chinese. My grandfather was Chinese, or came from Guangdong. Yeah, so you know, quarter Chinese. That's my hair's Chinese here. So this is my where I like to be. It's the classroom with you all, and so I have you for 1 hour today, and we're going to talk about reservoir modelling and resource assessment. Okay, so some of you will know a lot of this material. Some of you will know not very much. I'm like all of our New Zealand team. We're very friendly, so it's okay if you interrupt and ask questions as we go. Okay. All right. Let's go, because I think we've got 60 slides to go. So we can relax, some we can go more quickly. All right. So we'll talk about. I'll tell you the ideas behind reservoir modelling, why we do it, what's important, and then I'm going to talk about conceptual models and digital conceptual models. We'll talk about the process, the reservoir modelling process, and the tools, and then we'll talk about how we make models, how we calibrate them, and then we talk about the forecast scenarios and some case studies, and then we'll move on to some more advanced topics around uncertainty quantification and resource assessment. So the thing about geothermal reservoirs, as I'm sure you all know already, is that we don't know the subsurface thermodynamic conditions. We do a lot of great work with our geoscientists to try to understand what they are, but the reality is that we're measuring. We only have a few points that we're measuring in the subsurface, down wells or at surface. And when we measure the downhole conditions, we're not measuring the reservoir conditions. And Anne Robinson-Tate mentioned that yesterday, and it's a really important point. You measure the well conditions, you're not measuring the reservoir. And so, and we can measure the flows, and we can measure things at the surface, and then what we can infer from our geophysical and geochemical, geoscientific data, seismic and things. And so the whole point is we don't know, we can't measure all the conditions in the subsurface, only at certain points. And so the idea of a geothermal reservoir model is to try to represent our understanding, reproduce what we think, how we think the geothermal system is behaving, testing ideas so we can understand how it behaves, and while we're agreeing with all of the data that we do have available. And so if we can do that and we can build good models, then they're very, very powerful tools for supporting decision making. And this is an example of a conceptual understanding of the Waiariki Tauhara geothermal system with upflows in red and it's a little bit unresponsive to pointer. So upflows from Tauhara in the red, and then the downflows in the blue. You can see the different topography of the different basements and lithology. And then this is our numerical model with the temperature distribution and the flow arrows showing the upflows coming up, and there's actually two upflows, one under Waiariki and one under Tauhara, and they flow together into the middle underneath this is actually where the Waikato River is. And so this is a map this is a map showing where the cross section is through sort of northwest through the geothermal system. So there's several steps in doing geothermal reservoir models. We need to gather, analyse all the data. We need to develop a conceptual model that represents our understanding of how the system's behaving. And then we need to create a reservoir model, calibrate the model, and then make forecasts to support our decision making. And so and these are iterative. So throughout the life of the of your geothermal project, you'll be constantly calibrating the model, feeding back information from your calibrated model back into the model development, running forecasts and feeding information back. So this is all iterative. And as you over time, you'll gather more data. So you have to go back to the beginning and go through this process over and over again. Okay. The really important part, which we mentioned yesterday, is that it was actually Andrew Ray mentioned that you need to the conceptual model, the numerical model. These need to be updated constantly as we get more information from our geoscientific surveys and our reservoir and engineering data. Okay. So, we talked about this yesterday, but just to go through it again. So, I co-lead the geothermal modelling group at the Geothermal Institute with Mike Sullivan, my dad, and he worked with Lawrence Berkeley National Lab back in 1980 on the original CO2 equation of state for TUF2. It wasn't called TUF2 back then, it was called MOLCOM. So he's been doing this for a very, very long time now, and is really one of the world leaders in geothermal reservoir modelling. We've got 10 full-time geothermal reservoir modellers. Angus is with me, he's one of them. and 2 full-time uncertainty quantification specialists. So we're pretty sure that makes us the largest, or one of the largest dedicated geothermal modelling teams in the world. And we have PhD candidates and interns and master's students working with us. So at any time there might be 20, 30 people dedicated to geothermal modelling in our group. And we work on these projects specifically not for research, but to support important decisions that stakeholders are making, like I'll talk about later in the talk. All right, so we've been working for the last almost 10 years now using an integrated modelling approach for geothermal reservoir modelling, and the idea is that you really want to combine together reliability and best practice. If you can do that, then you're going to get value delivered from your modelling. The modelling shouldn't just be an exercise that you tick the box so that you can go to the lender or the financing team and get money for the development. You really should be, to get the value out of the modelling, you want to make sure it's done well and following best practice. And if you can do that, I mean, the reliability piece, what you want is robust, proven approach is what we do. We've tested and benchmarked how we do our reservoir modelling really extensively. And the key thing is that we use a very transparent and transferable approach. So we were in Chengdu with Itri and the team last year, and we showed them exactly how we do everything, because there's no advantage to having a closed approach. It's really important that it's transparent and transferable if this is going to be successful for the industry. In terms of best practice, our approach, we build into our integrated modelling approach to work very, very closely with the geoscience team, and that ensures that we get all their expertise built into our models. Okay, and it's not just the geoscience team, but the engineers, the management, all the decision makers, and by doing that, you not only support evidence-based decision making, but you get really good buy-in from all of the stakeholders by having an open best practice approach. And if you can do all that, then you get the value from the modelling. You get real confidence in your decisions, and that contributes to the success and sustainability of the project. And you get that confidence not just from having a good model, but from following a really robust integrated modelling approach. Okay? And so this is an old picture I did for, I think this was for the ITB conference in 2016, so it's getting a little old, but it's still true. So what we have is, at the centre is the conceptual model that Andrew was talked a lot about yesterday, and all of those the geoscientific, hydrology, environmental, and engineering data that feeds into that, and then we use Leapfrog from Sequent and some of our tools, which I'll talk about, PyTough and Tim, to couple that tightly to our numerical model. Now, our geothermal reservoir model is a combination of the natural state model, the production history model, and the future scenarios. And we use AUTough2, Waiwera, PyTough and Tim, which I'll talk about. And it's a two-way coupling, so the numerical models feed back to the conceptual model and vice versa, but they're very tightly coupled. And by using this approach where we really have this tight coupling to the conceptual model, as I said, it really ensures that all of the expert knowledge is included in our numerical models. It improves the communications of the models when you're talking about modelling results or model development. The geoscientific team, the management team, they understand what you're talking about. And a really key thing, I think, for here in Taiwan as well, is that this approach allows early model development and rapid progress. You know, our esteemed colleagues yesterday, the senior colleagues were talking about we've got to move fast, we've got to move fast. So being able to, by using this robust, proven approach, you can do things quickly. All right. So what's a conceptual model? So this is, Andrew did great stuff already and talked about it in the Taiwanese context as well, but I'll just run over it quickly. So it's a schematic representation of a geothermal reservoir in the wider system, and it should include all of these things: temperature distribution, pressure and hydrology, some indication of the permeability, particularly major structures and pathways. It should have some indication of geology and alteration. We're looking for information about where the fluid phases, so where it's going to be liquid, where we think it might be steam. That's what all of these little bubbles are showing, where we think the steam zones are. And we should have indications of some of the chemistry. So it's talking about, it's chloride neutral here in this example. And you should have some of the surface chemistry too, surface discharges, and then the fluid flows. So the arrows showing the upflows and recharge and downflows. So this is an example by one of our good friends, Greg Usher at Jacobs. And there's a few things. With a conceptual model, it has to be physically possible. Okay, the whole idea is that you're proposing some understanding of how the system behaves. It has to actually be possible. So it needs to take into account the boiling and buoyancy and density effects of the properties of water. It's important that it respects all the data, and that's why when you get new data, you need to update your conceptual model to make sure it agrees with all the data you have. You need to be thinking about the natural flows. A really important difference between geothermal reservoirs and oil and gas reservoirs are geothermal reservoirs are always connected in some way to the groundwater and the larger recharge. They're not closed, confined reservoirs. Sometimes the connectivity can be very low, but they are always connected, okay? And you should make some effort to think about the uncertainty. And this is an example from a paper by Bill Cummings. So it's showing two different possible conceptual models based on the available information, which in this case is just exploration data from the surfaces and probably some MT to give a couple of possible representations of the smectite clay alteration. And then these are giving one example of a sort of a possibility. One possibility is a mature geothermal system with a two-phase reservoir, and another one is an example of actually it could be explained by a fault-hosted hot upflow and into some sort of lava breccia. So that's a way of proposing the possibilities in your conceptual models. Okay, so what's a digital conceptual model? Well, those are really important, those cross-sections and maps that we draw for our conceptual models. But these days what we use is 3D modeling software. And we do a lot of work with Sequent and using Leapfrog. And so then we'll be pulling in all of the data, like all the topography data and geochemistry information, the geology and the structures, so you can see the lithologies here and representations of the structures, the geophysics representing conductivity, resistivity, and interpreted alteration as a result of that. And we pull that together with all of our well logs and also any temperature data to make these nice 3D representations of how we think the system is behaving. And in Leapfrog Energy with Sequent, it's really a very nice tool for looking at your digital conceptual model. It's easy to make slices. It's easy to move views and make movies, which are great for stakeholders' engagement and understanding. And you know, these are the kind of high-resolution images that you can make that really, you know, give you good detail on the shape of the hot convective plume, information about the clay cap and the drilling and the lithology. So they are really, really useful tools. I found when we started doing this, it was really interesting how quickly non-technical stakeholders engaged with projects when we gave them nice 3D representations of what we think was happening in the subsurface. It's amazing how much a fairly short movie can convey about a complex idea. This is one my student made. This is Flores in Indonesia, and so these are geological maps, and these are the faults that were interpreted from the geological surveys and studies, and then that's just the basement. This is the deeper sedimentary formation, and then we have some tertiary volcanics, and then some mid-quaternary volcanics, or lower quaternary, mid-quaternary, and then finally the younger volcanics on top. And then this is the interpreted clay cap based on the MT. It's a bit wobbly. I think the MT was a little challenging, but you know, this movie was made by one of my master's students as part of his project. So it's really, these digital conceptual models are really powerful for conveying ideas, and they're a key component for having that tight coupling to our numerical models. And the stakeholders can see clearly what you're doing in your digital conceptual model. They can see clearly how it relates to the numerical model, and then that really helps with confidence in the modeling process. Okay, so the reservoir modeling process, the whole idea is we are going to solve conservation of mass and energy equations. I won't give you any equations today. There's going to be no test with any calculus or anything, so don't panic. And we solve the two-phase Darcy's law which governs the flow through porous media. And then the idea is that you're trying to match the measured data through the calibration process. So this is actually the our Ohaki model. So this is a cross section through it going down to about 3,500 metres deep, and you can see again there's an upflow that sort of splits into two parts as it gets into the shallower reservoir. And so as I said, there's the natural states. There's a natural state which is what we think the geothermal system was doing before people start changing things. So that one thing is definitely drilling production wells and producing. That will change a reservoir. But it can be even, we have examples like Rotorua in New Zealand, where the indigenous people of New Zealand, the Māori people, they've been using that resource for many, many years prior to industrial extraction. In fact, and there isn't any electricity production from Rotorua. So there are different ways that people can change a reservoir before making electricity. So the natural state is before any of that happens. And that's another thing that's very different to oil and gas reservoir modelling. There's no such thing as a natural state in oil and gas. You just assume the properties that are static at the start, whereas a hot convecting geothermal system is already moving at the start. It may be we consider it to be steady, which is not necessarily geologically accurate, but it's a reasonable approximation. But it may be steady, but it's still moving. The fluid is convecting, even though it's steady. And then we run the production history, which is where we represent what's happened since people have started drilling wells and changing the reservoirs conditions. And then you run forecast scenarios. And the calibration process, you have to calibrate the natural state, you have to calibrate the production history, and it's iterative and circular, so that if you make changes to fit your production history, you have to go back and rerun your natural state. And every time you change your natural state and production history, you need to rerun all your future scenarios again. So for our tools, so to do all of this, you need a reservoir simulator, a geothermal reservoir simulator. Now, there are many different geothermal reservoir simulators out there in the world. The most famous is TUF2, is the industry standard that was developed at Lawrence Berkeley National Lab. It's about 40 years old, so it's an old code, but it's a testimony to the robust algorithm that it is effective. Since with improvements in modern computing, we've now got some new, better tools. There's TUF3 from Berkeley. We have AU TUF2, so we've always collaborated with Berkeley and made a lot of improvements to TUF2 over the years, which means that we have our own version, which is a bit more efficient and a bit better. Then we have Waiwera, which is our open source geothermal simulator, which is a modern parallel code that we developed in partnership with GNS Science. And then there's Tetrad and Eclipse, and Volsong is another New Zealand reservoir simulator. And these are the ones, AU TUF2 and Waiwera are ones that have been developed at the Geothermal Institute. So, as I said, all of our tools are free and open source. AU TUF2 is free if you have a TUF2 license from Berkeley. TIM is our open source visualization tool, which Angus developed. He's responsible for that code, and I'm very grateful for that. And then PyTUF is a scripting library which we use extensively. Again, it's free and open source. And then Waiwera is our new, 5-year-old reservoir simulator that's free and open source. So, as I said, it's parallelized, so you can run very large simulations very quickly. It's free. We released it officially in 2019, and as I said, it's developed at Auckland in collaboration with GNS. It uses the PETSI libraries, which are that does all of the heavy lifting for the numerics and for the parallelization, and it's a scientific toolkit that comes out of Argonne National Lab in the US, so there's a very strong support base for that. And we've benchmarked that extensively, so there's some references at the end of my talk where you can go to and find we've done all of the appropriate tests to show that it's accurate and effective. So we use this code on all of our commercial projects. I've got several models running in the cloud as we speak. And it was designed explicitly to replace Tough 2. So it's got the same algorithm as Tough 2. So it gives you the confidence that you're going to get the same results as the industry standard, just a lot quicker. This is just a bit of computer science, nerdy stuff for you. So on a typical sort of production history model, about 88,000 blocks. On Tough 2, it was taking, about 8 hours to run on a single computer. I mean, it's, there's a lot of complex physics that's trying to be solved. And why if we on 1, 2, 8 cores, 2, 4, 8 cores, you can see already on one core we get a lot of speed up, and that's because of improvements in the solver. And then obviously if you run it on 8 cores on your desktop, you're down to about 20 minutes from 8 hours. And then when we start running it on an HPC, on one of the New Zealand supercomputers, we get it up to 40 cores, and it's down to about 7 minutes or 8 minutes. So there's a big difference from 8 hours to 8 minutes, obviously, and that means that you can start doing things in a much more efficient way. What you can see here, these sorts of models are not, this is the scaling. Ideally, you get on this line where you use more processors and it keeps speeding up. But for this sort of size model, you can't get too much faster than about 8 minutes because the model's not big enough. And that was on this production model of San Jacinto, which was for a project with Jacobs and Polaris in Nicaragua. So this isn't research. This is a real production model that they're showing those results for. And thank you to Jacobs and Polaris for letting us share those results. Now, a really big thing that happened in the last 2 years is we've moved that simulator into the cloud. We had been running it on New Zealand's supercomputer. Yes, I said supercomputer singular. We only have one. You're very lucky in Taiwan. I imagine you've all got supercomputers at home. But in New Zealand, we've only got one or two, but they're sort of connected. And that was fantastic. We couldn't have done it without the support of the New Zealand's e-research institute. But 2 years ago, we made the leap with AWS to take it into the cloud, and the results are fantastic. You get access to the latest CPUs in Amazon, and they worked really hard with us to set up virtual clusters. And so then we're running the same simulations or larger simulations here. These are about 3 times the size, and you see on the HPC we're running it on 80 cores across 2 nodes. It was taking about 870 seconds, and while we're on AWS in the cloud on 192, well, I'd say 96 cores, which is a single node, we're down to 600 seconds, and then we're still getting speed up when we do it on 2 nodes. So this is a game changer. Being able to run realistic production models in sort of 8 minutes in the cloud without having to own a supercomputer from anywhere in the world, being able to run them from anywhere in the world is completely going to change how we do reservoir modeling in the geothermal industry. And this is, as I said, this isn't coming, this is now. We're already doing this on our projects, and it will become best practice, because once people see we're running models in 8 minutes, no one wants to sit around and wait hours for them anymore. And it's just that the fact that you can do this everywhere, and it's cost effective. So those models, those 80,000 block models, they cost less than $1 to run. Okay, so it's really, really efficient, and effective. And the key thing that I want to talk about is not only that you can run really big high resolution models, but more importantly you can run thousands of models at once, because the cloud is embarrassingly parallel, is the phrase in English. It means that you can, if you want more models, you just ask AWS or Azure for more computers. So it really unlocks the idea of being able to do uncertainty quantification, and that means you can make much more robust decisions. We talked a lot yesterday about the uncertainties you have in your geothermal systems in Taiwan because of the early stage of development. Well, the best way to address that uncertainties is using reservoir modelling, where you consider all of the possibilities before you make important, expensive decisions. Okay, so those are the tools. Now how do we build the models? So we need to, the whole idea is you want to capture as much of the real system as possible, and you want to avoid as many bad assumptions as you can. And this is a key one. You need to have models that can deliver results on time. It's not, this isn't just research for research's sake. We need to have a way that we can get results to the stakeholders on time. So there are limits on the size of the models you can make. We always model to the surface because this removes the need to make assumptions about some constant pressure water table, and it means that you get an accurate representation of the shallow pressures and boiling. And I know that, like in a lot of countries, the natural geothermal resources, the hot pools are important, and so if you want to understand them and make sure you're protecting them, you need to be modelling to the surface. So we always model to the surface. One thing is that you need to make sure your model is large enough so that the edges of the model don't affect your forecasts. So we say at least 4 or 5 kilometres from the edge of the resistivity boundary. Be very careful of open boundary conditions, that they can give very inaccurate results. So you need to be very careful. We apply heat and mass at the bottom of our models to represent the deep geothermal upflow. In the past, people used to use constant pressure and temperature. Some people still do. You have to be very careful of those as well. Having a constant pressure temperature source at the bottom of your model can also overestimate production. And you want to make sure that the bottom of your model is far below the lowest production feed zones. So a few things is, so if this is your resistivity boundary from your geophysics, you want models, this model's too small, you want more room around it. This one's no good because you're too close to the edges. You want to have it nicely centered with enough room around it to capture the natural recharge. Okay, so then you need to include some representation of your geological units. So this is where we use our digital conceptual model to map our lithological units directly onto our numerical model. So we have here our geological model, 3D geological model, and that mapping straight onto the numerical model. One of the things is if we don't have information when you're building this, often especially at an early stage, like in Taiwan, you'll have some drilling, some interpreted cross sections, but we need to fill all of the space of the numerical model needs some lithology assigned. So it's the geoscientific team's job to make some estimates of the areas where you don't have information. Often our geology students in particular say, but we don't know what's there for sure, so how can we guess? And I say, well, we've got to have it in our numerical model. So either you guess or I'm going to guess, and I'm an engineer. So it's better that you have an educated guess as a geologist than I do, okay? Also, we always include all of our possible structures explicitly in our model. So we have almost, it's not a discrete fracture network model, but it's like that idea. So all the major faults and structures are represented explicitly, and we make sure we follow sensible geological rules, like a fault can't increase the permeability across the strike of the fault, because it can only act as a barrier across the strike, and it can only act as enhancing permeability up the dip and along the strike. And we use the geophysical data to generate interpreted clay caps. So that comes from the 3D resistivity, but also the well logs and temperature logs as well. Another thing that we've been doing, and we published this last year, is we use a standardized modeling framework. So that means that all of our models are set up in exactly the same way. That's really helpful because then you can move them around your team. You can share tools for plotting, setting up models, and it means that also means that your stakeholders get familiar with the way models are presented, and so that's really positive as well. We use a set of version-controlled Python tools for doing that, and that gives us end-to-end model setup, calibration, forecasting, and uncertainty quantification. And we use a standard database of JSON files, which are human readable and computer readable to store all of the measured data. And this is, like I said, it means that we can do rapid development. It means that the models are always set up correctly and consistently and quickly. And all of the inputs are transparent for the stakeholders. It's very easy to show the stakeholders what's going into the models. Okay, that's how we set it up. Then how do we calibrate it? So we take all of our measured field data. The initial data is what we use to tell us about the conceptual model and the natural state. And then the transient production data is what we use for calibrating the production. So at this stage in Taiwan, we'll be looking mostly at this sorts of data and then possibly some early production flow testing, etc. So things like the geology, geochemistry, geophysics, hydrology, exploration wells, the first early production wells, downhole temperatures, surface features are all feeding into these conceptual model natural state. And then later on we'll look at changes in reservoir pressures, production flow rates, enthalpies, downhole temperatures and their changes, and changes in geochemistry, gravity, things like that. So, as I said, with the natural state model, we're trying to estimate the thermodynamic conditions before there's been any changes from production. And so, we assume they're steady states, which is an approximation, but it's not an unreasonable one. And you do this kind of process. So we set up our model, we run it, we load the model results, we compare them with the measured results and look at the difference. We analyze the results, we make changes to that maybe the location and strength of the deep upflow and the permeability distribution. We save our model and we run it again. And this is the kind of thing you see. These are downhole temperature plots, so depth versus temperature. So this and the dots are the measured downhole temperatures. And say we've got the red line as one model and the blue line is our next attempt. And the idea is you want to try to match your model up to your measured data. Okay? And then with the production models, what we do, we're trying to estimate how those thermodynamic conditions in the subsurface change when we start producing. So they have to start from our natural state. So our natural state model gives us our initial temperature, pressure, saturation, and flow conditions. Because like I said, it's not static, it's dynamic. The natural state model is already dynamic and moving. And what we need to do, you need to put all of the production and reinjection wells into your model. So you need to know where their likely feed zones are, you need to know the well designs, the well completions, and you need to put them into and represent them in the model. And you'll have things like measured production data, so this is flow rates, and that's an input. You tell the production model this is how much fluid was produced, and then the calibration data is the measured enthalpy, so the dots there, and then the line is the forecast, the model's match to them. And that's a pretty good match, you know. It needs a little bit more calibration, but it's not too bad. And then similarly, you've got things like here where we've got measured reservoir pressures, are the dots, and the blue line is the reservoir response, and that's a very good match to that pressure decline. Okay? And so these are the steps You set up the production history model with the well, all the well history using the natural state model. You run the production model, load the model results, compare the production enthalpies and reservoir pressures with measured data, analyze the results, and then you go back and you make changes to the permeability and the porosity in the natural state model. And then you've got to go run the natural state model again and go right back. Because if you change your model permeability porosity distribution, well then the permeability distribution will change what your natural state temperature pressure distribution looks like. So you have to go back and rerun the natural state. And we use dual porosity models as standard for our production histories in our future scenarios. So we are representing the fracture flow as in non-equilibrium with the matrix flow for production, which is important for when you're trying to understand reinjection or enthalpy changes. So we do that as standard. Okay, a couple of points on model calibration. It's never finished. So my dad, Mike, Professor Mike Sullivan, he's been calibrating the Wairaki model for 35 years. So it's never finished. You always get new data and you need to improve your model. There's always room for improvement. And it's really about the amount of time, money and effort you need that's required or what you're trying to answer. So it's limited by time and economic conditions to how well it's calibrated. I think anyone who's done any geothermal reservoir modelling knows you end up calibrating up to basically the last day you can before you start producing results for the client. One of the things is it's often very time consuming to get the last 5% matching very well. And so it's often not worth putting all that effort into improving the calibration, especially given the assumptions and uncertainties that are inherent in geothermal reservoir models. And it's really important to always think, what are you trying to understand? And make sure that you're doing an appropriate amount of calibration and that your calibration objectives align with the questions you're trying to answer. Perhaps you're most focused on a reinjection strategy, or you're looking to drill your first production well, so you're doing well targeting. Think about what you're trying to achieve when you're doing the calibration. And so we use calibration metrics now, so we can automatically assess how well a model matches the data, and that can be helpful. And we do use some inverse modelling at times. Our friends in Iceland like inverse modelling. It can help, but it's not a magic bullet. Be very careful. If you're hoping that you can just give a model to an inverse modelling tool and hope it will calibrate it for you, you'll be very disappointed. Okay, so we've done all of that. We've calibrated our model as best we can in the time we have. Now it's time to make some forecasts. And so the whole point is that we can run models that can predict the future thermodynamic conditions. Time's up, crikey. It says here I've only been going 43 minutes. I reckon I've got 17 more minutes. So I'm going to keep going. So it's things like this. So we look at this is the historic steam flow, and then we want to look at how the reservoir will respond if we're going to increase production up to a certain level. And so these are vital tools for planning a geothermal development. So these are the kind of things we use it for. How long we can economically exploit a system, what's the schedule of new makeup wells we need to maintain production, how we're going to respond to different rates of production, how we're going to best re-inject fluid, how to protect the natural geothermal features, or how they're going to react, what other environmental effects might occur, like subsidence or something like that. What's the resource potential of a system? And I'll talk a bit more about this, it's particularly important. And then this new one which I mentioned yesterday, which is how we can extract minerals from the system as well as energy.
John, I do think it was a shorter time slot.
Oh.
40 odd minutes.
Really? I was sure it was an hour when I planned it.
Like any good lecturer.
Oh. Okay, we'll go pretty quickly then. Do you think our model forecast will be correct? No. All models are wrong, but good models are useful, okay? So every model has assumptions, and the subsurface is too complex to represent them all perfectly, okay? So it's important to understand what you can't do for a reservoir. So I'll go through this quickly and then we'll have to skip over the rest. I'm sure it was an hour. I must have looked at an earlier schedule. So drilling success. This one always disappoints the drilling engineers. But the truth is, reservoir models cannot predict the probability of drilling success. There's too many other factors involved. They can't tell you exactly where to drill. They can't predict exactly where the good permeability is. And they can't predict problems with casing, cementing, or anything like that. And they can't predict exactly the well performance before drilling. But a good reservoir model with good data can tell you where the high hot enthalpy fluid is most likely to be. It can predict where the good average permeability exists. And it can predict the future well performance very well once you've done some initial testing. In terms of operation, they can't predict any operational problems. You can't predict mechanical failures or human error. I once had people ask me, well, why would we drill new wells if the price of oil is dropping? And they definitely can't predict the price of oil, so there's no economics in these models as standard. But they can help you plan contingency on resource availability and predict the effect of unexpected long-term changes in production. Okay, I'm going to skip through this because we're going to have to finish up. I think I can share the slides with anyone who wants to just get in touch with me. We've been doing a lot on supercritical modelling as well, modelling hotter and deeper, and modelling multiple geothermal systems. We're also looking at reducing risk by modelling all the way down to the deep roots of a geothermal system, so we don't need to make assumptions about where that deep upflow is. I talked yesterday about some of our projects at Wairaki Tauhara. I was going to give you more details about these ones in Indonesia, and this is a low enthalpy project for district heating in France. And then the lithium extraction we talked about. Okay, so we talked briefly about this as well, but this is really important. So the idea that you can run thousands of models very quickly, and we use mathematical tools to then assess how well each of those models fit the data, and we can use any sort of data to work out how well various models fit what with a conceptual model. And you get these sorts of like new plots where you can look at the probability of encountering boiling. This is a cross-section through a geothermal system, a model where we can predict where we're going to find boiling or different temperature regimes. And the main thing is, like we said, you get these forecasts. So this is an example where all of the little grey lines are all the different model samples. Each one of them is a full geothermal model, and there are, and then the little dots are the measured data. So you see all of the models match the measured data pretty well, and then when we forecast forward, we get a spread of forecast. Now in this case, the spread's not very much because we don't add any new wells, so it's fairly tight. It's still, a bit of a range of about 5 megawatts. But then here's the case where we drill a whole lot of new wells, and you can see you get a much wider range of possibilities, and we're able to give the management P90s, P10s, which are much more powerful for them for the decision making on how much to invest and planning for the costs. And I talked about this yesterday, replacing the stored heat calculation with doing uncertainty quantification for reservoir models using only the exploration data. And this is a really powerful new tool where we essentially we generate thousands of models. So a month ago we ran 5,000 models for a new system in an afternoon on Amazon. It cost about $1,000 to do it. But then we can look at all of the ones that generate plumes that fit the clay cap, and we can use those to forecast forward about the resource potential. All right, I better wrap up. So It's an invaluable tool for predicting the reservoir behaviour. It's really important to understand what you're trying to do with the models and what the limitations are of your models. It's really important to ensure they're consistent with the conceptual model and that you update the conceptual models. The uncertainty quantification that we're pioneering is really giving us much more robust forecasts, and it really is going to become standard practice. And we really think there's some real value in using it for these much more accurate resource assessments. Make sure you get whoever does your modelling for you, make sure it's done following best practices, and some of the regulators and policy makers in the room will probably start requiring it. My dad and I contributed to a book which is a good place to start. Be really cautious if the modelling always gives you the answers you want, you know? It's a bad sign if you always get the answers you want from the model. Start modelling early. Gather really good data, as much good data as you can during the project and at the start and throughout, and continuously update your data model to get the value out of it. Now, I'll just finish with an analogy. So if you think about your geothermal system like a sports team, or any team, then in New Zealand we love rugby. Unfortunately, this is the Springbok team winning the World Cup last year, not us, we were second. It used to be us in that picture, but it will be again, don't worry. But so, you know, in your geothermal project, the managers, they're like the coaches and managers of your professional sports team. The wells are like your superstars, the players. They're what make the money. They're the most important thing to make a team successful. You need the wells. You need the resource. So, you know who this person is back here? No, neither do I. They're the physiotherapist. So they're not important. No one knows their name. They're not really paid very much either. But no professional sports team starts without a physiotherapist, right? Checking the well, checking the peak players, making sure they can play. And they don't just check them at the start of the season and then leave. They're there the whole season checking. And that's us. We're the testing engineers and the reservoir engineers. That's our job. We're the physiotherapists. We make sure things are okay to start, and we're there the whole time to make sure it keeps going well throughout. And look, compared to the other costs in a geothermal project, I think for about an hour of drilling, you can get a lot of modelling done these days, okay? So you know, thank you very much. Tēnā koutou katoa. I'd just like to acknowledge Science Spectrum National Lab, Sequence, AWS, and New Zealand's MB for their support. Sorry for running over.